Hi everyone! Today let's talk about session 1.6, substitution method. We have learned how to solve first order ODE, which is either separable or linear. Today we will illustrate substitution methods that sometimes can be used to transform a given differential equations into one of the form that we already know how to solve. For example, the separable or linear ODE. So given a first order nonlinear, non-separable ODE, so we have dy dx equals f of xy. Suppose f of xy appears to be a composition function. And so it's like the chain rule we have learned in Calculus 1. We can let v be the inner function of a composite function, and we can solve y in terms of v. Okay? And then we try to get ODE about v. And then we can solve the ODE using separable method or the integrating factor method. Then we can substitute the y back. Okay, let's see how to solve it. Now we have example 1, dy dx equals x plus y plus 3 squared. And now you can see the right hand side is a composite function where the inner function is x plus y plus 3. So then we let this guy be v. Okay, so the first step, let v be x plus y plus 3. Okay, this is the inner function. Second step, solve y in terms of v. So, well, we can just move the x and 3 to the other side. So we get minus x minus 3. Now, what happened? Okay, next we want to get ODE about v. So on the left hand side, you see dy dx. So what is dy dx in terms of v? Now, look at this equation. We take the derivative with respect to x on both sides. On the left hand side, we have dy dx. On the right hand side, we have dv dx minus derivative of x is 1 and derivative of minus 3 is 0. Okay? Now, we can plug in. So we can plug in this guy here. Then we have dv dx minus 1 equals v squared. Now you see, this is an ODE about v. Okay, how to solve this? It's nonlinear ODE. Let's change it to the standard form. So dv dx equals v squared plus 1. And you notice that the right hand side is a function of v, right? So it's separable. Now we can both sides divided by v squared plus 1. So v squared plus 1 equals dx. Now we can integrate both sides. Oh, okay, let me make this smaller. I don't have enough space. Okay. Okay, so now let's see. We integrate both sides. On the left, we see this is the arctangent. So arctangent of v equals integral 1 is x plus c. Okay, and in this case, we can actually solve for v. So v is then tangent of x plus c. And what is v again? V is x plus y plus 3. Now solve for y. Y is then tangent x plus c minus x minus 3. So this is the solution to this differential equation. Okay, so this is the fourth steps. Okay, we solve the differential equations here because it's separable, so we use the separable method, and then after we get a solution of v, we put the y back, so then we can have a solution of y. So far so good. Okay, let's continue. Homogeneous equations. We learned the definitions of homogeneous equations for linear ODE in session 1.1. Here is a different definitions of homogeneous equations for nonlinear first-order ODE. Okay, do you remember the definition for linear ODE? Well, that is, we have the operator Ly equals 0, so we just have the right-hand side is 0. Then we get homogeneous linear ODE. Okay, for nonlinear ODE, a homogeneous equations is one that can be written in the form of, so dy dx equals f of the function y over x. Okay, and now you can see this is a composite function. So then we can make the substitution. We can let v be y over x. And then y is going to be v over x. And then when we differentiate, we use product rule. So product rule, what happened? We get v times the derivative of x is 1 plus x times the derivative of v with respect to x. Okay, now we can plug in. So the left hand side we can replace by this guy. V plus x dv dx equals f of v. Okay. And sometimes students get confused. Okay, sometimes students get confused. They might think, oh, can we set v equals x over y instead of y over x? Let me show you what happened. If you let v be x over y, then y is x over v. Wow! When you differentiate it, this is quotient rule. Right? Do you like quotient rule? No. So that's why we only let v be y over x, not x over y. Okay? We love product rule and we don't want quotient rule. Okay, so that's the reason. Alright, so let's look at this example. And another property of the homogeneous equations, if you have power terms, polynomial like that, okay, and then you can see the degree of each term are the same. So you can see this guy, x degree 1, y degree 1, so the total degree of this term is 2. And then this guy is degree 2, this guy is degree 2. So it's like all the terms have the same degree. So if we have like power functions. All right. Okay, so what do we do? In the first step, we want to solve for dy dx. So we divided both sides by 2xy. So 4x squared plus 3y squared over 2xy. And keep in mind, we want to express this in terms of y over x. So let's split them. So 4x squared over 2xy plus 3y squared over 2xy. Alright, this guy, one of the x cancel, and 4 and 2 cancel, we get 2. So we get 2x over y, plus here the y cancel, so 3y over 2x. Okay, now we're ready because we let v be y over x, and then we get y equals vx, and then dy dx product rule. Okay, so dv dx times x plus v times the derivative of x is 1. Okay, now we can plug in. So we have dv dx times x plus v equals 2. So this guy, x over y, is actually 1 over v. Okay, maybe let's put 2 over v. Plus this guy is 3 over 2v. So far, so good, everyone? Okay. Oh, do you see we can both sides subtract v? Then we have dv dxx is 2 over v. This guy subtract v become 1/2 v, right? And let's see. So let's combine them, okay? And we get the denominator is 2v, and then here 2 times 2 is 4 plus v squared. So this is actually separable, right? You can see this is a function of v and this is the function of x. Move the function of v to the left, and we divided by 4 plus v squared and times 2v equals we divided by x. Okay, so let's integrate both sides. On the left hand side, you can see the derivative of the denominator is 2v dv is exactly the numerator, so we can use u substitution. So let this be a u, this is du, so the integral of du over u is ln of absolute value of u. But in this case, because this guy is always positive, so we don't need to have the absolute value. And integral of 1 over x is ln absolute value of x plus c. Okay, now we can both sides raised to the e power. So what happened? And e and ln cancel, so we have 4 plus v squared equals e and ln. Oh, you can consider this guy is e to the ln of x times e to the c. Okay, e to the e and ln cancel, so absolute value of x times e to the c. You can get rid of the x and then rename e to the c by a new constant. This can help us to get rid of the absolute value. Okay, so rename. Maybe let me do it in 2 steps. Rename a new constant to get rid of the absolute value. Okay, now what happened? What is v? V is y over x. So 4 plus y over x squared became y squared over x squared equals x times d. So if you don't like to see fractions, you can both sides multiply by x squared. Then we have 4x squared plus y squared is dx cubed. So this is the solution. Okay, so if you want to continue, you can solve for y, right? Okay, so this is the example 2, okay, about homogeneous nonlinear differential equation. Okay, let's continue to look at example 3. Example 3, you can see this is degree 1, this is degree 1. This is square, but when you take the square roots, it's also like degree 1. So first of all, let's figure out what is dy dx. So both sides divided by x. Y over x plus x squared minus y squared divided by x. We can move the x inside the square root. And then we have x squared minus y squared over x squared. What is that? Well, split them, x squared over x squared is 1, and then we have y over x squared. Okay, so see, we have expressed the right-hand side as a function of y over x. Now we're ready. Oh, by the way, when you watch the lecture videos, before we look at each example, feel free to try it first, okay? And then continue to play the video and to check your work. Okay, so let's see. We have v equals y over x, and then so y equals v times x, dy dx equals dv dx times x plus v, derivative of x is 1. Okay, so put this into the ODE, then the left hand side is dv dx x plus v. The right hand side we have v plus square root of 1 minus v squared. Oh, do you see what happened? The v cancel. And we can both sides divided by square root of 1 minus v squared. And divided by x. And multiplied by dx. See, this is separable. Alright. On the left hand side, if you can remember, this is the sine of v. The right hand side is ln of absolute value of x. Plus c. Oh, how do we find v? Sine. Applying sine on both sides. Okay. And v, what is v? v is y over x. So what is y? X times sine of natural log of absolute value of x plus c. And oh, we have initial condition. So y of x0 is 0. Okay, we can plug in here. So x is x0 greater than 0. Okay, we put that in. v is y over x, so that is also 0. X sine of 0 is 0. And ln of x0 plus c. So c equals minus ln of absolute value of x0. And you know x0 is positive, so that's why we don't need absolute value in this case. Okay, so now finally y is x sine of ln of x, absolute value of x for minus ln of x0. Okay, so this is the final answer. And sometimes if you want to simplify it, you can notice that the ln, you can actually combine them. Okay, why is that? That's the property of natural log. So let me put it here. Natural log of a times b is natural log of a plus natural log of b. Natural log of a over b is natural log of a minus natural log of b. Okay? Alright, so let's continue. So the next type of differential equations is the Bernoulli equations. A first order differential equations of the form, okay, dy dx plus p of xy equals q of x y to the n. Do you see this is the extra term y to the n? Okay, so our regular linear first order ODE, then we don't have y to the n. So the Bernoulli equations, we have this extra factor on the right hand side. So this is y to the n. And we need to make sure n is not 0 and n is not 1. If n is 0, then because if n is 0, we just get the linear ODE. If n is 1, then we have the y. Then we just move to the left hand side and combine with the p of x. We also get linear ODE. Okay, then we can, for linear ODE, we can just use the integrating factor method. Okay, so that's why if we have y to the n on the right hand side, we said this is Bernoulli equation. And this is a substitution we're going to make. We let v to be y to the 1 minus n. Okay, now what happened? How do we solve for y? Well, y is you both sides and then have the apply to the both sides to the 1 over 1 minus n, and this guy cancel. Then we have y, right? So that's why you get y equals v to the 1 over 1 minus n. And then how do we differentiate? Well, dy dx. Well, this guy is what? Chain rule, right? So v to the this guy, you put the exponent down in front, and then you have v to the that exponent, subtract 1 times v prime. So here we're using chain rule. Okay, and then put this into the differential equation. You get, okay, let's see. You get 1 over 1 minus n, v to the, here, this is the same as 1 minus n, and then 1 minus 1 plus n, right? If you take the common denominator 1 minus n, and then we still have dv dx. And then this guy plus p of x, y. Y is v to the 1 over 1 minus n equals q of x. Y is v to the 1 over 1 minus n, but because y to the n, so we put n on top. Okay, now you can see this guy cancel. Let's see. Okay, so we want to make the coefficient of dv dx is 1. So let's see. Both sides multiply by 1 minus n. We get v to the n 1 minus n dv dx plus 1 minus n p of x. V to the 1 over 1 minus n equals 1 minus n q of x. V to the n over 1 minus n. So now both sides divided by this guy. Then we have dv dx plus, okay, now let's see. Divided by this is the same as we subtract the exponent n over 1 minus n. Okay, and then the right hand side, because this is the same, the right hand side, we just get 1 minus n times q of x. And what is this? Oh, you can combine them. You get 1 minus n over 1 minus n. That's exactly 1. So that's why eventually you get this formula. Okay, in the exam, this formula will be provided. Okay, but you can think about, it's very easy. The extra term factor is just you put 1 minus n in front of p and q, and that's it. This is the only change. Very similar to the the regular linear ODE. Okay. All right. Then because now this is a new linear ODE about v, we can solve it using integrating factor method. All right, so let's continue. Now we do example 2 using this method. Okay. Let's see. First of all, we want to express in that form of Boolean equation. So both sides divided by 2xy. And now let's see what happened. Oh, do you see this y square and y cancel? And because this is there's one y here, this is like the linear term, we move to the left. We get dy dx minus 3 over 2xy equals x cancel, so for 2 divided by 2 is 2, so 2x times y to the minus 1. Okay, because we want to express in this form y to the some power, so that's why move it in the numerator to become y to the minus 1. Okay, now compare. So compare to this is the Boolean equation standard form. Now we get this is p of x, this is q of x, and this guy is the n. N is minus 1. Okay, then by the Boolean equations, we know we're gonna let v to be y to the 1 minus n is minus 1. So y squared. Then we gonna get, okay, we're gonna plug in here. So this formula, we get dv dx plus 1 minus n is -1, so become 2. P of x is -3 over 2x. V equals 1 minus n, which is 2, times q of x. Q of x is 2x. Okay, now let's see what happened. 2 cancel, so we get dv dx minus 3 over xv equals 4x. Okay, now this is a linear ODE, but this guy is the new p of x. This is the new q of x. So when you use the integrating factor, you're not using the original p of x, q of x, because you want to solve this linear ODE. Okay, I don't have enough space. Let me make this guy smaller. Okay. Okay. So, all right. So now we continue. Let me use a different color so you know. So now mu of x is e to the integral, the new p of x, which is minus 3 over x dx. This is e to the minus 3 ln of absolute value of x. And let me guess what this is. Absolute value of x to the minus 3. And here, because we don't have initial conditions, so just assume x is positive. So we get x to the minus 3. So far, so good, everyone. Okay, by the integrating factor formula, y, but here, this is the ODE about v. So v times integrating factor equals integrating factor times q. Q is 4x. Yes. So we have 4 times x to the minus 2. Well, what do? We add 1 to the exponent divided by that exponent. Alright. And how do we solve for v? Both sides multiplied by x cubed. So we get minus 4x cubed times this guy is x squared plus c times x cubed. And what is y? V is y squared. So we get y squared equals minus 4x squared plus cx cubed. So this is our answer. And let's check this answer. Let's see whether this guy is the same with our example 2. Okay, so keep this in mind. Example 2. Are they the same? Yes, they're the same. It's just like we move this guy to the other side, become negative, and this here we have the D, but that example we have the C. Okay, so they are the same. So same with answer in example 2. And it makes sense because it's the same ODE, we just use different way to solve it, and of course we get the same solution. Okay, everyone. Now, please pause the video and work on example 5. Are you ready? Okay, let's check our work together. So first thing, make it into the standard form. So both sides divided by x. So 6 over xy. Here, x cancels, so 3y to the 4/3. So this is p, this is q, and the n is 4/3. Okay, so v is y to the 1 minus n, so 1 minus 4/3. That is y to the minus 1/3. Okay, And then our formula dv dx plus 1 minus n, which is minus 1/3, p, which is 6 over x v, equals 1 minus n, which is minus 1/3, times q. Okay, so this is the same as saying dv dx minus 2 over xv equals minus 1. And then this is our new p of x, and this is our new q of x. Now this is the linear first order ODE of v. Okay, now we can use the integrating factor method. Integral minus 2 over x dx. What is this? 2 ln of absolute value x. And what happened? What is this guy? This is absolute value of x squared. Sorry, to the negative 2y. Okay, let me do it one more time with you. We raise to the minus 2 here, then these cancel. And because here we don't have initial condition, we just assume x is positive. So x to the minus 2. Okay, then the formula is x to the minus 2v equals integral x to the minus 2 times q, so which is minus 1. Oh, this is x to the minus 1 over minus 1. They cancel. So, and what is v? Multiply both sides by x squared. Then we have x plus cx squared. And what is v? V is y to the negative 1/3. Okay? And if you want to solve for y is, you both sides want to raise to the minus cube. So we get x plus cx squared to the minus cube. So this is the final answer. Do you have the same answer? Yes. Okay. The typical mistake is students will use the O, P, and Q. No. You need to use the new P and Q. Okay. Right. Let's continue. So please pause the video and work on example 6. Have you finished? Okay, let's see. Do we have the standard form? Nope. So both sides divided by 2x. dy dx. Let's see. Plus e to the minus 2x divided by 2x y cubed equals y. Alright. So, we gonna both sides, let's see, because this is the linear term, so we should move this to the left. So we have dy dx minus y equals negative e to the minus 2x, and then over 2x, and then y cubed. Okay, then p of x is minus 1, q of x is this giant term, and then n is 3. Alright, so v is y to the 1 minus n, so y to the negative 2. Okay, and then dv dx plus 1 minus n, which is negative 2, times p, which is minus 1, v equals minus 2 times q. Okay, so this is dv dx plus 2v equals 2 cancel, minus cancel, e to the minus 2x over x. Okay, now this is our new p. This is our new q. So the integrating factor, e to the integral 2 dx, e to the 2x. Alright, so v times the integrating factor equals integral, the integrating factor times the q. Oh, do you see what happened? They cancel. Integral of dx over x is ln of absolute value of x plus c. So v is y to the negative 2. Okay, so you can leave it like that, or you can solve for y. Okay, so if the problem asks you to solve for y explicitly, then you can keep going and solve for y. So far, so good, everyone. All right. Do you want to know how to solve for y? Okay. So you have both sides divided by e to the x, e to the 2x, and this guy means 1 over y squared. So y squared, you're gonna flip the right hand side, and then you take square root. When you take square root, you get plus or minus. Okay, so this is how to solve for y. Do you have the same answer? Alright, let's continue. Example 7. Do you see the right hand side is a composite function? Well, we just let v be the inner function. Alright, so remember 4 steps. First, let v be the inner function. Second step, solve for y. Well, y is then v plus 4x. And what is dy dx? Dv dx plus derivative of 4x is 4. And then now we can plug in to get ODE about v. On the left hand side, it becomes dv dx plus 4. On the right hand side, this is v squared. Okay, so dv dx equals v squared minus 4. Okay, this is a separable ODE. Both sides divided by v squared minus 4. Both sides multiplied by dx. Okay, on the right hand side it's easy because it's just integral 1 is x plus c. But on the left hand side, okay, do you remember how to do this guy? This is rational function, so partial fraction. Yes, partial fractions. Remember, we need to factor the denominator completely. How do we factor this guy? V plus 2, v minus 2, right? Remember, we have 4 cases. First, distinct linear factor. Second, repeated linear factor. Third, distinct irreducible quadratic factor. Fourth case, repeated irreducible quadratic factors. Okay, so they are in Calculus 2, session 7.4. So if you completely forget what partial fraction is, you can go to my Calculus 2 website and go to session 7.4 and watch the lecture videos and notes. Okay, so we're gonna solve this use partial fraction. So this is 1 over v plus 2, v minus 2. We want to decompose it as sum of simple proper fractions. So linear factor, they are all case 1. So you put proper means the degree of the numerator is less than the degree of the denominator. So the general form, constant over v plus 2 and constant over v minus 2. And then multiply both sides by the common denominator. We have a times v minus 2, b times v plus 2. And then we have two variables. We need two equations to solve the two unknown. So pick v is 2. Then do you see what happened? This guy becomes 0. And then right hand side for b. So b is 1 over 4. And when we pick v equals minus 2, we get minus 4a. And this guy is 0. So a is minus 1 over 4. Okay, so if you see a lot of linear factors, you just after you multiply by the common denominator and clear all the denominators, you want to pick the value such that the linear factor is 0, then you can see a lot of terms are 0, and then you can solve for that unknown constants, ABC, okay? Now we get the left-hand side. What is the left-hand side? The left-hand side is now a is minus 1 over 4, and then we have dv over v plus 2 plus 1 over 4b, and then dv over v minus 2. So, well, chain rule. This is ln of absolute value of v plus 2. This is ln of absolute value of v minus 2. So far, so good, everyone. And let's see. And oh, that's it, right? So the whole thing, put them all together, equals x plus c. So what is v? V is y minus 4x. So minus y minus 4x plus 2, y minus 4x minus 2 equals x plus c. Okay, so this is the solution to this differential equation. Okay, now we have finished session 1.6. If you have any questions, feel free to ask me. Have a nice day. Bye.